Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here. Maybe you've had a long day, perhaps your mind is racing with thoughts that won't quiet. Or maybe you're simply the kind of a person who finds comfort in drifting off to thoughts of the cosmos rather than counting sheep. Whatever brought you to this moment, to this exploration, you're exactly where you need to be. Before we begin our journey tonight, if these calm explorations of the universe help you unwind or spark your curiosity as you drift towards sleep, consider liking and subscribing. It helps others find their way here too, one curious mind at a time, one peaceful thought at a time. Tonight, we're venturing into territory that exists at the intersection of wonder and warning, into the darker corners of the universe where beauty and danger dance together in ways that would terrify us if we truly grasped their scale. We're traveling to the places where stars don't just shine peacefully in the night, but threaten, where the death of distant suns, events so far away that their light takes thousands of years to reach us, could nonetheless reach across the vast emptiness of space to touch our world with invisible fingers of destruction. We're talking about the most dangerous stars in the cosmos, the stellar giants and compact objects that could, under precisely the wrong circumstances, wipe out life on Earth in an instant. Or perhaps more terrifyingly, erase it slowly, methodically, without warning or mercy. Think about that for a moment. Right now, as you lie here listening to these words, somewhere in our galaxy a massive star is in its final moments. Its core is collapsing. Forces beyond human comprehension are gathering, preparing to unleash energies that will outshine billions of normal stars. And when that explosion comes, when the star dies in a burst of radiation and light, that deadly energy will begin its journey outward, traveling at the speed of light, crossing distances measured in thousands or tens of thousands of light years. It might pass us by harmlessly, just another cosmic event in a universe full of them. Or it might not. It might be aimed our way, a cosmic bullet fired millennia ago, already in flight, already on its way to Earth. The universe, for all its breathtaking beauty, for all the wonder we feel when we gaze up at a star-filled sky on a clear night, is not a gentle place. It never has been. Between the glittering points of starlight that inspire poets and the soft glow of distant nebulae that fill us with awe, there lurks potential catastrophe on scales that make our terrestrial disasters seem quaint by comparison. Massive stars spinning at the edge of collapse, having exhausted the nuclear fuel that kept them stable for millions of years. Dense stellar remnants with magnetic fields so powerful they literally warp the fabric of space itself. Fields so intense that the very atoms in your body would be torn apart if you ventured too close. Binary systems locked in death spirals that will end in collisions releasing more energy in a fraction of a second than our sun will produce in its entire 10 billion year lifetime. And, perhaps most unsettling of all, there are the focused beams of gamma radiation, invisible cosmic rifles that could be pointed our way right now, at this very moment. Their triggers already pulled millions of years ago, the lethal light already traveling through space toward us at exactly 100,000 kilometers per second. There's no way to see them coming. No early warning system sophisticated enough to detect them before they arrive. The first indication of danger would be the danger itself. gamma rays slamming into Earth's upper atmosphere, triggering a cascade of chemical reactions that would unravel the delicate balance of gases that makes life possible on this world. We live our lives, all of us, every human being who has ever existed, under skies that seem peaceful, constant, eternal. We watch the sun rise and set with reliable precision. We see the same constellations our ancestors saw thousands of years ago, barely changed, seemingly permanent. The moon waxes and wanes on its predictable schedule. The planets wander their ancient paths through the zodiac. Everything about the night sky suggests stability, permanence, safety. It's easy to feel that the cosmos is a benign backdrop to our lives, pretty but inert, beautiful but ultimately separate from our daily concerns. But the astronomical record, the deep history written in stone and starlight, tells a very different story. Earth has been bathed in deadly radiation from cosmic explosions before, multiple times. Ancient rocks, when examined with sensitive instruments, preserve evidence of stellar cataclysms that touched our world millions of years ago, depositing radioactive isotopes that could only have come from supernova. Mass extinctions in the fossil record, sudden die-offs that eliminated vast swaths of life in geological instants, may bear the fingerprints of dying stars from across the galaxy. The history of life on Earth is not just a story of evolution and competition, of predators and prey, of climate shifts and ice ages. It's also a story of cosmic accidents, of bad timing, of being in the wrong place when the universe decided to remind us of its power. We live our lives under skies that seem peaceful, constant, eternal. But the astronomical record tells a different story. Earth has been bathed in deadly radiation from cosmic explosions before. Ancient rocks preserve evidence of stellar cataclysms that touched our world millions of years ago. Mass extinctions in the fossil record may bear the fingerprints of dying stars from across the galaxy. Life on Earth exists, has always existed, at the mercy of forces so powerful, so distant, and so utterly beyond our control that we can only watch, measure, calculate probabilities, and hope that when the next cosmic catastrophe occurs, it happens, far enough away to leave us in peace. It's a humbling thought, isn't it? All of human history, all of our wars and empires, all of our art and science and philosophy, all of it unfolding on a world that could be sterilized by an event that happened thousands of years ago in a place so distant we can barely comprehend the separation. An event we wouldn't even know about until its consequences were already upon us, already remaking our atmosphere, already triggering ecological collapse. So let your breathing slow now. Let your muscles relax, your thoughts quiet, your body grow light as if gravity itself has softened its hold on you. Let your mind open to the scale of what we're about to explore. The dangers we'll discuss tonight are real, documented, understood by science. They're not science fiction or wild speculation. These are actual phenomena, governed by known physics, happening right now in our galaxy and across the universe. But they unfold across timescales that dwarf human lifetimes, across distances that make interplanetary space seem like a short walk. Understanding them doesn't make us unsafe. Understanding them doesn't mean we should live in fear. What it does is give us perspective. It connects us to the larger story of our fragile world spinning through a universe that is at once both our cradle and our potential doom. Tonight, we'll travel together through the gallery of stellar threats, each one more powerful than the last, each one capable of reaching across the void to touch our world. From gamma-ray bursts that can strip away our atmosphere in seconds, to magnetars with magnetic fields strong enough to disintegrate matter at the atomic level. From collapsing supergiants that will explode with the brightness of a billion suns to colliding neutron stars that forge gold and platinum in the crucible of their destruction. We'll discover that the universe, beautiful as it undeniably is, never forgets to remind us how small we truly are, how contingent our existence, how dependent on factors far beyond our influence or control. Now, let's begin. Gamma-ray bursts, the universe's deadliest weapon. If you were to ask astronomers what single cosmic event poses the greatest threat to life on Earth, many would answer without hesitation: a nearby gamma-ray burst. These events are the most energetically powerful explosions known to occur in the universe since the Big Bang itself. In a matter of seconds, a gamma-ray burst releases more energy than our Sun will produce over its entire 10 billion-year lifespan. That sentence bears repeating, because our minds struggle with the scale. One star, in one final moment of a collapse, can outshine hundreds of billions of stars combined. And all of that energy, all of that fury, can be focused into beams narrower than a searchlight. Concentrated enough to kill worlds across thousands of light-years of space. Gamma-ray bursts were discovered by accident during the Cold War. American military satellites, designed to detect Soviet nuclear tests in space, began picking up mysterious flashes of gamma radiation. These weren't bombs. They were coming from deep space, from distances so vast that the light from some of these events had been traveling toward Earth since before our solar system existed. The discovery opened a window into one of the universe's most violent phenomena, and it revealed just how dangerous the cosmos can be. We now know that gamma-ray bursts come in two main varieties, and both are born from stellar death. The long-duration bursts, lasting more than 2 seconds and sometimes stretching to minutes, come from the collapse of massive stars. These are stars at least 20 to 40 times more massive than our Sun. Giants that have burned through their nuclear fuel in just a few million years, and now face the ultimate consequence of their size. When such a star exhausts the fusion reactions in its core, there is no longer any outward pressure to resist the inward crush of gravity. The core, an iron sphere about the size of Earth but weighing more than our Sun, collapses in less than a second. This collapse is so rapid, so total, that the iron atoms are crushed into their constituent protons and electrons. The electrons are forced into the protons, creating neutrons and releasing floods of ghostly neutrinos. What remains is either a neutron star, matter compressed to densities we can barely comprehend, or something even stranger, a black hole, a rent in space-time itself. But the collapse doesn't happen smoothly. The infalling material from the star's outer layers rains down onto the newly formed compact object, swirling into an accretion disk of matter heated to billions of degrees. this is where the magic and the horror happen. The spinning disk, threaded with powerful magnetic fields and rotating at significant fractions of the speed of light, acts like a cosmic accelerator. Matter falling toward the center is funneled along the star's rotational axis, squeezed by magnetic fields into two narrow jets that punch through the collapsing star's outer layers. These jets, moving at more than 99% of the speed of light, bore through thousands of light-years of stellar material and burst into space like cosmic blowtorches. And along these jets pour torrents of gamma rays, the most energetic form of light in the universe. When a gamma ray burst is pointed directly at Earth, the results could be catastrophic, even from distances that would otherwise seem safe. The gamma rays would not penetrate deeply into our atmosphere, true. They wouldn't cook the surface of the planet or boil the oceans. But they wouldn't need to. What they would do is far more insidious. As gamma rays slam into molecules in the upper atmosphere, they split apart nitrogen and oxygen, creating nitrogen oxides. These compounds are extraordinarily efficient at destroying ozone, the molecule that shields all surface life from the sun's harmful ultraviolet radiation. Computer models suggest that a gamma ray burst from within about 6,500 light-years if aimed at Earth could strip away 25 to 50% of our ozone layer in a matter of seconds. The burst itself would be over almost before it began, lasting perhaps 10 seconds. There would be no warning. The first indication of the catastrophe would be the burst itself, arriving at the speed of light with no herald, no advance notice. One moment the sky would be normal, the next satellites would fail. The ionosphere would light up with auroras visible even in daylight, and high-energy particles would begin cascading through the atmosphere. But the real damage would come in the hours, days, and months that followed. With the ozone layer depleted, ultraviolet radiation from the sun would pour through to the surface at levels far higher than any life evolved to withstand. The effects would be felt first in the oceans, where phytoplankton, the foundation of the marine food web, would die en masse. These microscopic organisms can't hide from the sun. They live in the upper layers of the ocean, photosynthesizing, producing oxygen, feeding everything from krill to whales. Kill the phytoplankton, and you collapse the entire oceanic ecosystem from the bottom up. On land, plants would suffer damage to their leaves and disrupted photosynthesis. Crops would fail. Animals, including humans, would face increased rates of skin cancer, cataracts, and immune system damage. The increased ultraviolet radiation would persist for years as the ozone layer slowly recovered, during which time the biosphere would be under constant assault. Food chains would collapse. Ecosystems would restructure. And if the burst were powerful enough or close enough, the effects might push life on Earth to the brink of extinction. The terrifying thing about gamma-ray bursts is their reach. A typical supernova, devastating as it is, becomes safe at distances of about 30 light-years. Its energy spreads out in all directions, following the inverse square law, weakening rapidly with distance. But gamma-ray bursts don't play by those rules. Because their energy is beamed, Focused along narrow cones perhaps only a few degrees wide, they remain dangerous across vast distances. A burst that occurred at 10,000 light-years away, if pointed at us, would carry the same threat as a supernova happening practically next door. And there's another disturbing factor. We can't predict them with any certainty. Oh, we know which types of stars can produce gamma-ray bursts. We understand the mechanics. But we can't look at a star and say, that one will explode in the next 1,000 years and point a beam at Earth. The universe doesn't give us that courtesy. The jets from gamma-ray bursts are narrow. Our galaxy is vast. The odds of a burst being aimed precisely at Earth are low, but not zero. And on cosmic timescales, low-probability events become near certainties. Astronomers have calculated that over the past 500 million years, there's roughly a 50% chance that Earth has been struck by a gamma-ray burst powerful enough to cause significant damage. Over the past 4 billion years, since life first took hold on our planet, that probability rises to 90%. It's not a question of if Earth has been hit. It's a question of when, how often, and how badly. And some researchers believe they've found the evidence in the fossil record, in an extinction event that happened 440 million years ago, when 60% of all marine life vanished in what we call the Ordovician extinction. We'll return to that story later. For now, just know that gamma-ray bursts are real. They're powerful, and given enough time, one will eventually point our way again. Wolf-Rayet stars, cosmic rifles pointed at Earth. If gamma-ray bursts are the bullets, then Wolf-Rayet stars are the loaded guns, sitting in our cosmic neighborhood, their hammers cocked, their barrels potentially aimed in our direction. These stellar monsters represent one of the final, most violent stages in the life of the most massive stars, and they're among the most dangerous objects known to exist in the galaxy. Named after the French astronomers Charles Wolf and Georges Rayet, who first identified their distinctive spectral signatures in the 1860s, these stars are the exposed helium cores of giants that have literally blown away their entire outer layers of hydrogen in stellar winds so fierce they make our sun's solar wind look like a gentle breeze by comparison. Imagine, if you will, a star that was born with 50 or 60 times the mass of our sun. For a brief few million years, cosmically speaking, barely the blink of an eye, it burns hydrogen in its massive core, shining with the combined light of hundreds of thousands, perhaps even millions of suns. The radiation pressure from all that luminosity, from all those photons streaming outward from the nuclear furnace at the star's heart, creates winds so powerful, so relentless, that they physically tear away the star's outer layers. We're not talking about gentle mass loss here. These stars can eject an entire solar mass worth of material, the equivalent of our entire sun, every single year. Some of the most massive Wolf-Rayet stars lose even more, multiple solar masses annually, driven by radiation pressure that quite literally blows the star apart from the inside out. Over time, measured in mere hundreds of thousands of years, the hydrogen envelope is stripped away entirely, peeled back like layers from an onion, revealing the superheated helium core beneath. What's left is a Wolf-Rayet star, an object that might now be, quote, only unquote, 10 to 20 solar masses, having lost most of its original mass to the stellar wind, but blazing with surface temperatures exceeding 50,000 degrees Celsius, more than 8 times hotter than our Sun's surface. At these temperatures, the star shines predominantly in ultraviolet light, invisible to human eyes but capable of ionizing gases across vast distances of space. The stellar wind continues, now carrying away helium and heavier elements like carbon and oxygen created by nuclear fusion in the exposed core. These stars don't live long, not by astronomical standards anyway. They've already exhausted most of their nuclear fuel in the furious burning that characterized their earlier phases, and what remains is being consumed at truly prodigious rates. A Wolf-Rayet star might persist for only a few 100,000 years, perhaps as little as 50,000 years for the most massive examples, before it exhausts the helium in its core and begins fusing even heavier elements in an increasingly frantic sequence: carbon, neon, oxygen, silicon. Each successive stage burns faster and faster than the one before. Carbon fusion, which in a smaller star might last for thousands of years, might proceed for only a few centuries in a Wolf-Rayet star, or even less for the most massive specimens. Oxygen fusion could take just a few months. And silicon fusion, the absolute final stage before the star creates iron and faces its inevitable doom, might last only days or even hours. The star is racing toward catastrophe, unable to stop, unable to slow down, driven by the laws of physics toward an end that has been predetermined since the moment it was born with too much mass. And then comes the end: core collapse, supernova, and quite possibly, quite terrifyingly, a gamma-ray burst. The iron core, having grown to a certain critical mass, perhaps 1.5 times the mass of our entire Sun, but compressed into a sphere no larger than Earth, can no longer support itself. The quantum pressure that has been holding it up, the degeneracy pressure from densely packed electrons, suddenly fails. The core collapses inward at roughly 1/4 the speed of light, imploding in less than a second from something Earth-sized to something the size of a city. The violence of this collapse, the sheer speed and totality of it, creates conditions found nowhere else in the universe outside the Big Bang itself. Temperatures surge to hundreds of billions of degrees. Densities reach values where atomic nuclei touch, where matter becomes a soup of subatomic particles. And from this maelstrom, from this churning chaos of collapsing matter and extreme physics, jets of material can be born, streams of particles accelerated to speeds approaching that of light itself, carrying with them torrents of gamma rays focused like death beams into narrow cones along the star's rotational axis. The danger Wolf-Rayet stars pose isn't just that they're going to explode. It's that they're going to explode in a very specific, very dangerous way. Because these stars are rotating rapidly and have powerful magnetic fields threading through their cores. When they collapse, the conditions are perfect for producing jets. The infalling material swirls into an accretion disk. The magnetic fields organize the chaos. And 2 beams of concentrated gamma radiation burst forth from the rotational poles, carrying death in a focused stream. There's a Wolf-Rayet star that keeps astronomers up at night. Its name is WR 104, and it sits about 8,000 light-years away in the constellation Sagittarius. That might sound far, but it's well within the danger zone for a gamma-ray burst. What makes WR 104 particularly unnerving is its geometry. This isn't a solitary star. It's part of a binary system, locked in orbit with a massive companion. As the two stars circle each other, the Wolf-Rayet star's powerful stellar wind spirals outward, creating a beautiful pinwheel pattern in space, a cosmic Catherine wheel of gas and dust that's been photographed by telescopes. Here's the problem. When we look at WR 104, we see that pinwheel nearly face-on. That means we're looking down the axis, the same axis along which the gamma-ray jet would be directed when the star finally explodes. It's like staring down the barrel of a rifle, and we don't know when the trigger will be pulled. The star could explode tomorrow. It could explode 100,000 years from now. The uncertainty is part of what makes it terrifying. If a WR 104 were to produce a gamma-ray burst pointed at Earth, the consequences would be severe. Even at 8,000 light-years, the burst would carry enough energy to deplete a significant portion of our ozone layer. The effects would mirror what we discussed earlier: mass die-offs of phytoplankton, ecosystem collapse, increased surface radiation, agricultural failure. It wouldn't be an instant apocalypse, but it would be a prolonged catastrophe, one that might well push human civilization to the brink. But here's where the uncertainty comes in. We don't actually know if WR 104 is pointed at us. The pinwheel structure suggests we're looking along the rotational axis, but along doesn't necessarily mean directly down. If the axis is tilted by even 10 or 15 degrees, the burst would miss us entirely. The beams from gamma-ray bursts are narrow, typically only a few degrees wide. Space is vast. Even small angular offsets translate to enormous physical separations at distances of thousands of light-years. So, WR 104 might be pointed at us, or it might not. We simply can't tell with enough precision. What we do know is that Wolf-Rayet stars are ticking time bombs. They're rare, thank goodness. Our galaxy probably contains only a few thousand of them, compared to hundreds of billions of stars overall. But they're out there, scattered through the spiral arms, and some of them are relatively nearby in cosmic terms. Gamma Velorum, one of the closest Wolf-Rayet stars to Earth at about 800 light-years, is another potential threat. It's actually a multi-star system containing a Wolf-Rayet star that will, someday, explode. Is it pointed at us? Probably not. But again, we don't know for sure. The winds from Wolf-Rayet stars are extraordinary in their own right, even before the star explodes. Material is being ejected at speeds of thousands of kilometers per second, fast enough that it crashes into the surrounding interstellar medium and creates shock waves that light up in X-rays. This wind-blown material, rich in carbon and oxygen from the fusion happening in the exposed core, eventually enriches the galaxy with heavy elements. Every atom of carbon in your body, every oxygen molecule you breathe, was likely created inside a star like this and scattered into space by its violent winds. But when the end comes, When the core finally runs out of fuel to fuse, the explosion dwarfs everything that came before. Wolf-Rayet stars don't produce ordinary supernovae. They produce hypernovae, explosions 10 or more times more energetic than typical stellar deaths. The kinetic energy alone from a hypernova can exceed 10 to the 52nd power ergs, a number so large it's meaningless to human intuition. These are the cosmic events that can be seen across the entire observable universe, bright enough to outshine their host galaxies for weeks. And if Earth happened to be in the beam when one of these hypernovae occurred nearby, there would be no hiding, no shelter deep enough, no magnetic field strong enough to deflect the onslaught. The gamma rays would arrive first, traveling at light speed, impossible to detect before they were upon us. Then, perhaps hours or days later, would come the high-energy cosmic rays, subatomic particles accelerated to nearly light speed by the supernova shockwave. These particles would penetrate deeper into the atmosphere, creating cascades of secondary particles that would increase radiation exposure at ground level. The good news, if there is any, is that Wolf-Rayet stars are rare, and gamma-ray bursts require very specific conditions to form. Not every Wolf-Rayet star will produce a burst. The star needs to be rotating rapidly. It needs to retain enough angular momentum through its mass loss. It needs to have the right magnetic field structure. Many Wolf-Rayet stars will simply explode as supernovae, still dangerous, but spreading their energy in all directions rather than focusing it into beams. And even when bursts do form, the beams are narrow. The overwhelming majority of gamma-ray bursts in our galaxy are pointed away from us, invisible threats that erupt and fade unnoticed, except by the unlucky systems directly in their path. But the possibility remains. Somewhere in the Milky Way, right now, there are Wolf-Rayet stars in their final years, their cores growing ever more unstable, their inner layers fusing elements step by step toward iron. Some of those stars will be the sources of the next gamma-ray bursts in our galaxy. And we won't know which ones until it's already happened, until the light from their explosions has crossed the intervening space and announced, 8,000 years too late, that another stellar monster has died. Supernovae, death throes of massive stars. Before we narrow our focus to specific nearby threats, we should pause to truly understand the broader category that encompasses so many of the dangers we face, supernovae themselves. These stellar explosions, even without the focused beams of gamma-ray bursts that make certain types especially dangerous, represent one of the most powerful and dangerous phenomena in the natural universe. There are the violent, spectacular deaths of stars that have reached the absolute end of their nuclear burning lives, having exhausted every possible source of fusion energy, and they're responsible for forging most of the heavy elements in the periodic table, including many that are absolutely essential for life as we know it. In a very real, very literal sense, we exist because of supernovae. Every atom of carbon in your body, every molecule of oxygen you breathe, every bit of iron in your blood, was created inside a star and scattered into space by a supernova explosion billions of years ago. But that doesn't make these events any less dangerous to life that has the misfortune of existing too close to one when it explodes. There are several distinct types of supernovae, classified by astronomers according to their spectral properties and the mechanisms that trigger them. But for our purposes tonight, for understanding the threats they pose to Earth, two broad categories matter most. Type 2 supernovae, also called core collapse supernovae, come from the deaths of massive stars, those at least 8 times the Sun's mass and often much more massive than that. These are the explosions that can, under exactly the right circumstances involving rapid rotation and strong magnetic fields, produce gamma-ray bursts. Type 1a supernovae, by contrast, come from white dwarfs, the dense but relatively small stellar remnants left behind when Sun-like stars too small to go supernova on their own, finally exhaust their nuclear fuel and shed their outer layers. When a white dwarf in a binary system siphons enough material from its companion star to push its mass over a critical threshold of about 1.4 times the mass of the Sun, a limit known as the Chandrasekhar limit, it can no longer support itself against gravity. The carbon and oxygen that make up the white dwarf ignite catastrophically in a runaway thermonuclear explosion that completely destroys the star, leaving nothing behind except an expanding cloud of debris. Type 1a supernovae are particularly important for cosmology because they all explode with roughly the same intrinsic brightness, making them useful as standard candles for measuring distances across the universe and understanding its expansion rate. But they're also potentially dangerous from a planetary safety perspective. The challenge, the thing that makes them particularly insidious, is that they come from white dwarfs, and white dwarfs are dim, easily overlooked objects. There are many white dwarfs in our galactic neighborhood, hundreds within a few dozen light-years of Earth, and their binary companions might not be immediately obvious to casual observation. A Type 1a supernova could theoretically go off disconcertingly close to Earth without much warning, from a system we didn't even realize was approaching the critical mass threshold, from stars we might not have been carefully monitoring. But Type 2 supernovae, the core collapse events that mark the deaths of massive stars, are what really capture the imagination and inspire the most profound concern among those who study cosmic threats to life. When a massive star, having lived for only a few million years compared to the billions of years smaller stars enjoy, exhausts the nuclear fuel in its core, having methodically fused hydrogen to helium, helium to carbon and oxygen, and continuing through an ever-accelerating sequence of fusion reactions, producing increasingly heavy elements all the way up to iron, it faces a fundamental crisis. Iron, you see, cannot be fused to release energy. In fact, fusing iron to create heavier elements actually consumes energy rather than producing it. This means the star's core, now transformed into a sphere of pure iron, about the size of Earth, but containing more mass than our entire Sun, has absolutely no way to generate the outward radiation pressure needed to continue resisting the inward crush of its own gravity. What happens next unfolds in less than a second. The iron core collapses, shrinking from something the size of Earth to something the size of a city. Electrons are crushed into protons, forming neutrons and releasing torrents of neutrinos. The neutrinos, normally ghostly particles that pass through matter as if it weren't there, are produced in such numbers and with such energy that they carry away 99% of the supernova's total energy output. A small fraction of those neutrinos interact with the infalling outer layers of the star, heating them and driving them outward in a violent explosion. The explosion sends a shock wave ripping through the star at speeds of tens of thousands of kilometers per second. When the shock wave reaches the stellar surface, it tears the star apart, flinging millions of solar masses of material into space. This ejected material, enriched with heavy elements forged in the core and created in the explosion itself, slams into the surrounding interstellar medium at velocities high enough to create shock-heated gases that glow in X-rays and radio waves for thousands of years. But it's the immediate effects of a nearby supernova we're most concerned with here. The ways in which such an explosion could reach across dozens of light years to affect our world. A supernova releases energy across the entire electromagnetic spectrum, from the longest radio waves to the shortest, most energetic gamma rays. The visible light alone, the photons we could actually see with our naked eyes, can outshine entire galaxies containing hundreds of billions of stars. If a supernova occurred close enough to Earth, it might appear as bright as the full moon in our night sky, or even brighter, dominating the heavens, casting shadows at midnight, visible even during the day as a brilliant point of light hanging in the sky alongside the sun. Ancient astronomers who witnessed supernova events, like the one that created the Crab Nebula in 1054 CE, recorded them as guest stars that appeared suddenly and persisted for weeks or months before fading. But the visible light, spectacular as it would be, is not the real danger. The real killers are the high-energy components, the X-rays, the gamma rays, and the cosmic rays. These high-energy photons and particles can penetrate deep into planetary atmospheres, initiating complex chains of chemical reactions that destroy ozone and create other reactive compounds like nitrogen oxides. Cosmic rays, which are actually high-energy protons and atomic nuclei rather than rays in the electromagnetic sense, are accelerated by the supernova shockwave to speeds approaching that of light itself. These particles can persist in the region around the supernova for tens of thousands of years, gradually dispersing through the interstellar medium, slowly spreading outward, creating an expanding sphere of elevated radiation that can affect any star systems unlucky enough to be in the vicinity. How close would a supernova need to be to pose a genuine existential threat to Earth? This is a question astronomers and astrobiologists have studied extensively, running computer simulations, building atmospheric models, trying to understand the full range of potential effects. The commonly cited figure, the number you'll find in most scientific papers on the subject, is about 26 light-years for a typical Type II supernova, based on detailed atmospheric modeling and careful observations of supernova remnants like the famous explosion that occurred in 1987 in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. At that critical distance of 26 light-years, the gamma-ray flux would be intense enough to strip away more than half of Earth's protective ozone layer. Not all of it, not enough to completely sterilize the surface, but more than enough to cause catastrophic ecological consequences. Life wouldn't end immediately in some dramatic Hollywood-style apocalypse. There would be no instant vaporization, no boiling oceans, no Death Star-style planet destruction. But the long-term effects, unfolding over months and years and decades, would be devastating nonetheless. The increased ultraviolet radiation penetrating through the damaged ozone layer would disrupt photosynthesis in plants, damage DNA in exposed organisms, trigger widespread mutations, cause ecosystem disruptions as entire food chains collapsed, led to massive agricultural failures as crops died in the fields under the unfiltered solar radiation. The cascade of consequences, each one triggering others in an ever-expanding web of ecological collapse, might well lead civilization, perhaps even our entire species, to the brink of extinction or beyond it. Fortunately, and this is genuinely fortunate because fortunately is doing a lot of work in this sentence, there are no massive stars currently within that critical 26 light-year danger zone. The nearest supernova candidate of any significance, the famous red supergiant Betelgeuse that marks the shoulder of Orion in the winter sky, is about 700 light-years away, more than 25 times farther than the minimum safe distance. At that range, Betelgeuse's eventual explosion, whenever it happens, will be a spectacular sight, a cosmic light show visible for months, but it won't pose a meaningful threat to life on Earth. But we must remember that the galaxy is a dynamic place, not a static snapshot. Stars orbit the galactic center at different speeds, following different paths through the spiral arms. Over millions and tens of millions of years, over the vast sweeps of geological time, the local stellar neighborhood changes dramatically. Stars that are currently far away might pass close by our solar system in the future. Systems we don't currently identify as threats might become threats as orbital dynamics bring them into our vicinity. And there's evidence, written in stone and ice and ancient sediments, that supernovae have affected Earth before. About 2.5 million years ago, during the transition from the Pliocene to Pleistocene epochs, radioactive isotopes like iron-60 were deposited in ocean sediments. These isotopes don't occur naturally on Earth. They're produced in supernova explosions and rained down on our planet from space. The pattern suggests that one or possibly several supernovae exploded relatively nearby, perhaps a few hundred light-years away. Did these explosions affect life on Earth? It's hard to say with certainty. The timing coincides with the end of the Pliocene, a period of global cooling and the onset of the Pleistocene ice ages. Some researchers have suggested that the supernovae could have triggered climate changes by increasing cloud cover or altering atmospheric chemistry. Others point to possible extinction events among marine megafauna. The evidence is tantalizing but not definitive. What is certain is that supernovae are not just astronomical curiosities. They're ongoing threats, rare on human timescales but inevitable on geological ones. Somewhere in our galaxy, a massive star explodes roughly once every 50 years. Most of these explosions are far away, occurring in the dense star-forming regions of the spiral arms tens of thousands of light-years from Earth. But occasionally, one happens closer to home, and when it does, we feel the consequences, even if we don't immediately recognize them. The radiation from a supernova doesn't arrive all at once. The initial flash, the optical brightening, comes first, traveling at light speed. Then come the X-rays and gamma rays, also at light speed but from different parts of the expanding debris. Days or weeks later, the cosmic rays begin to arrive. Subatomic particles that have been accelerated to near light speeds by the supernova shockwave, but which travel slightly slower because they follow curved paths through the galaxy's magnetic fields. If you were standing on Earth when a supernova exploded 30 light-years away, you might see it brighten in the night sky over the course of hours or days. If it were close enough, it could become as bright as the full moon, visible even in daylight. Depending on where it appeared in the sky, it might seem to hover near the horizon or shine from high overhead. In ancient times, such an event would have been terrifying, interpreted as an omen or a portent. Now, we would understand what we were seeing, but that understanding wouldn't make us any safer. The effects would begin within days. Satellites would start detecting increased radiation levels. The ozone layer would thin. Within weeks, ultraviolet measurements at the surface would rise. And then would come the slow, grinding consequences. Crop failures, ecosystem disruptions, increased cancer rates, the collapse of food webs in the ocean. These effects might persist for years, even as the ozone layer gradually recovered. Life would adapt, as it always has, but not without cost. Betelgeuse and nearby supernova candidates. Let's talk about Betelgeuse, a name you've almost certainly heard even if you're not particularly interested in astronomy. It's one of the most famous stars in the night sky, instantly recognizable to anyone who can find the constellation Orion the Hunter rising in the eastern sky during winter evenings. Betelgeuse marks the eastern shoulder of the giant, the bright reddish star that forms one corner of the distinctive hourglass shape that makes Orion so easy to identify. The name itself comes to us from Arabic, possibly a corruption of Yad al-Jawza, meaning the hand of the central one, though the etymology is debated among scholars. For millennia, humans have looked up at this star, telling stories about it, using it to navigate, marking the seasons by its rising and setting. For decades now, probably longer if we're honest, astronomers have known that Betelgeuse is a red supergiant star in the late terminal stages of its life, having already exhausted the hydrogen in its massive core and moved on to fusing heavier elements. It's already fused hydrogen to helium in a core that once burned with temperatures of millions of degrees. That helium has itself been fused to create carbon and oxygen. And now, in its twilight years, it's engaged in the increasingly frantic process of fusing those heavier elements into even heavier ones, creating neon and magnesium and silicon and eventually, inevitably, iron. The star is massive, truly massive, estimated at somewhere between 15 and 20 times the mass of our Sun. If you were to somehow transport Betelgeuse to the center of our solar system, replacing the Sun with this red supergiant, its outer atmosphere would extend beyond the orbit of Mars and possibly reach Jupiter. It's genuinely enormous, one of the largest stars we can observe in our region of the galaxy. Someday, and astronomical speaking, that someday might mean tomorrow, or it might mean 100,000 years from now because these timescales become fuzzy and uncertain when dealing with stars in such advanced evolutionary stages. Betelgeuse will explode as a supernova. The iron core at its heart will grow too massive to support itself. The core will collapse. The outer layers will rebound in a catastrophic explosion, and for a brief time, measured in weeks or perhaps months, Betelgeuse will shine with the light of hundreds of millions of suns. The question that's captivated both professional astronomers and the general public alike, the question that gets asked every time there's news about Betelgeuse, is simply, when? In late 2019, and continuing into early 2020, Betelgeuse underwent what astronomers described as an unusual, unprecedented dimming event. The star, which had been one of the 10 brightest objects in the night sky for as long as human records existed, faded dramatically. It dimmed to less than half, perhaps as little as 40%, of its usual brightness. To casual observers, people who glance at Orion without really studying it, the change might not have been immediately obvious. But to anyone who knows the sky well, to amateur astronomers with their backyard telescopes, to ancient sky watchers who would have memorized the brightness of every major star, the change would have been striking, undeniable, impossible to miss. Speculation ran wild, spreading through social media and astronomy forums and science news websites faster than facts could keep up. Was this it? Were we witnessing the beginning of the end? Were we about to see a supernova, a once-in-a-civilization event that would be visible even in daylight, that would dominate the night sky for months, that would be photographed and studied and marveled at by millions of people? Astronomers around the world, professional and amateur alike, trained their telescopes on Betelgeuse with unprecedented intensity, monitoring it across multiple wavelengths from radio to X-ray, trying to determine what was happening, trying to understand whether this dimming presaged an imminent explosion or was just another quirk of a star already known for its variability. As it turned out, after months of observation and careful analysis of the data, the dimming was almost certainly caused by the star ejecting a particularly massive cloud of dust that temporarily obscured our view of the stellar surface, like a particularly thick and extensive patch of cosmic smog that happened to lie between Earth and Betelgeuse. Betelgeuse didn't explode. It hadn't even begun the final collapse sequence. It recovered its brightness over the following months, returning more or less to normal levels, though normal for Betelgeuse is a relative term since the star is known to be variable, pulsating and changing in brightness on various timescales. But the episode highlighted something important, something that makes astronomers both excited and slightly frustrated. We don't really understand the late stages of massive star evolution as well as we'd like to think we do. These giant stars in their death throes are unpredictable, prone to outbursts and variations we can't fully explain, following evolutionary paths that are clearly more complex than our models account for. The good news is that Betelgeuse is far enough away that its explosion, while spectacular, won't threaten life on Earth. At roughly 700 light-years distant, the supernova would be magnificent to observe. It might reach a peak brightness comparable to the full moon, dominating the night sky for weeks or months. It would be visible during the day, a brilliant point of light hanging next to the sun, and it would provide astronomers with a once-in-a-lifetime opportunity to study a nearby supernova in unprecedented detail. But it wouldn't be dangerous. The gamma rays from the explosion would spread out in all directions, following the inverse square law. By the time they reached Earth, having traveled 700 light-years, they would be too diffuse to cause significant atmospheric damage. We might see a small uptick in cosmic ray flux. There might be beautiful auroras as charged particles from the supernova interacted with Earth's magnetic field. But there would be no mass extinction, no collapse of the ozone layer, no threat to life. Betelgeuse is a red supergiant, which means its explosion will likely be a Type II supernova. These explosions spread their energy relatively evenly in all directions. They don't produce the focused gamma-ray jets that make Wolf-Rayet stars so dangerous. So, even though Betelgeuse is close and will definitely explode, it represents more of a celestial spectacle than a genuine threat. The same cannot be said for all nearby supernova candidates. Ik Pegasi, a binary star system about 150 light-years away, contains a white dwarf that's accreting material from its companion. If that white dwarf gains enough mass to reach the Chandrasekhar limit of 1.4 solar masses, it will explode as a Type Ia supernova. These explosions are more powerful than typical Type II events, and 150 light-years is uncomfortably close, well within the potential danger zone. However, current models suggest that Ik Pegasi's white dwarf is not massive enough, and the accretion rate is too slow for an explosion to occur anytime soon. By the time the white dwarf could become a threat, the system's motion through the galaxy will have carried it to a safer distance. So, while Ik Pegasi is worth monitoring, it doesn't represent an immediate danger. What about other candidates? Spica, in the constellation Virgo, is a massive binary system about 250 light-years away. Either of its stars could potentially go supernova, though again, they're far enough that the threat is minimal. Rigel, the bright blue supergiant in Orion, is about 860 light-years away and will explode someday. But at that distance, it too poses little danger. The real concern isn't necessarily the stars we know about, it's the ones we don't. White dwarfs, as we've mentioned, are dim. Binary systems containing white dwarfs can be hard to detect. There could be systems within the danger zone that we simply haven't identified yet. And while the odds of a nearby white dwarf going supernova in the next 1,000 or even million years are low, they're not zero. This is where we talk about the galactic habitable zone, a concept analogous to the habitable zone around a star. Just as planets need to orbit within a certain range of distances from their star to maintain liquid water, star systems need to occupy a certain region of the galaxy to be safe from cosmic catastrophes. Too close to the galactic center, and you're exposed to higher radiation levels, more frequent supernovae, and the disruptive gravitational effects of the supermassive black hole and the dense stellar environment. Too far out in the galactic halo, and there might not be enough heavy elements for rocky planets to form. Earth sits in what appears to be a relatively safe zone. We're about 26,000 light-years from the galactic center, orbiting in a minor spur between two major spiral arms. This location has several advantages. The density of massive stars is lower here than in the spiral arms, reducing the supernova rate. We're far enough from the galactic center to avoid most of the radiation and disruption from that direction. And our orbit keeps us near what's called the corrotation radius, where our angular speed around the galaxy matches the rotational speed of the spiral density waves. This means we spend more time between spiral arms than passing through them, again reducing our exposure to supernovae and other stellar hazards. But the galaxy is not static. Stars move, spiral arms evolve. Over hundreds of millions of years, what is safe today might not be safe tomorrow. The Sun's orbit takes it above and below the galactic plane in a slow oscillation. As we pass through the denser parts of the disk, we're exposed to more potential threats. Some researchers have even suggested that mass extinctions on Earth might be correlated with these passages through the spiral arms, though the evidence remains controversial. What we can say is this: right now, at this moment in cosmic history, we're relatively safe. The nearby stars that could go supernova in the near term are all far enough away that their explosions won't threaten us. But near term in astronomy means thousands to millions of years. We can't predict what the galactic neighborhood will look like a million years from now, let alone 10 million or 100 million. Stars will be born and die. Some will pass close to the solar system. Others will recede into the distance. The configuration of threats around us will change, slowly but inevitably. This is the nature of living in a dynamic galaxy. Safety is temporary. Danger is statistical. And the long-term fate of life on Earth depends not just on what we do here, on our little world, but on forces operating across scales we can barely comprehend, in places so distant we can only see them as points of light in the night sky. Magnetars, the most magnetic objects in the universe. Now, we venture into territory that seems almost like science fiction, like something dreamed up by writers trying to imagine the most extreme objects possible, but which is very much science fact, confirmed by observations and understood through rigorous physics. Magnetars are neutron stars, those incredibly dense remnants left behind after certain types of supernova explosions. But they're neutron stars with a literally mind-bending twist, a property so extreme it pushes our understanding of physics to its absolute limits. They possess magnetic fields so powerful, so incomprehensibly strong, that they completely defy everyday intuition and make Earth's magnetic field look laughably weak by comparison. These fields are measured not in single Gauss or even thousands of Gauss, but in the hundreds of trillions of Gauss, sometimes reaching quadrillions. To truly grasp how absurd these numbers are, how far beyond human experience they reach, consider this. Earth's magnetic field, the one that allows compasses to work and protects us from solar wind, measures about half a Gauss at the surface. The strongest continuous magnetic field ever created in a laboratory by human technology, achieved using superconducting magnets and requiring enormous amounts of electrical power to maintain, is about 45 Tesla, which translates to 450,000 Gauss. That represents the absolute pinnacle of our technological capability when it comes to generating magnetic fields. A magnetar's magnetic field is roughly 1 trillion times stronger than our best laboratory efforts. 1 trillion times. The number is so large it becomes almost meaningless to human comprehension, like trying to imagine the size of the galaxy by counting grains of sand. What happens in the presence of such an unimaginably intense magnetic field? The answer is genuinely disturbing. Physics as we understand it from everyday experience changes fundamentally. The very atoms that make up ordinary matter are distorted beyond recognition, their electron clouds stretched and deformed by the magnetic forces acting on them. If you were somehow able to approach within about 1,000 kilometers of a magnetar's surface, assuming you had some magical protection against the radiation and heat and tidal forces that would kill you long before that point, the magnetic field would be strong enough to completely warp the atomic structure of your body at the molecular level, atom by atom, molecule by molecule. The chemical bonds that hold proteins together would be disrupted. The electrical signals that allow your neurons to fire would become impossible. Your biochemistry, the intricate dance of chemical reactions that keeps you alive from moment to moment, would simply stop working. You would die not from heat or radiation in the conventional sense, but from the fundamental breakdown of the chemistry that defines life. From the impossibility of maintaining the molecular structures that make a living thing different from a collection of random atoms. But you'd never get that close. Long before you reached the magnetar itself, the radiation would kill you. These objects emit powerful X-rays and gamma rays. Their surfaces can crack under the stress of their own magnetic fields, releasing bursts of energy that can be detected across thousands of light years. And when magnetars undergo what's called a starquake, a violent rearrangement of their crust, they can release more energy in a fraction of a second than the sun produces in years. The most famous magnetar outburst occurred on December 27, 2004. SGR 186-20, a magnetar about 50,000 light-years away on the far side of the Milky Way, underwent a massive starquake. The event released about 10 to the 40th joules of energy in 1/10 of a second, equivalent to the sun's entire energy output over 150,000 years. The gamma-ray flux from this explosion was so intense that it disturbed Earth's ionosphere, affecting radio communications despite the enormous distance. If that same event had occurred at a distance of just 10 light-years instead of 50,000, the effects on Earth would have been catastrophic. The radiation would have stripped away much of our ozone layer, possibly triggering a mass extinction. It would have been equivalent to a nuclear explosion high in the atmosphere, but with no warning and no defense. The question that's troubled astronomers for years is, how do magnetars form? We know they're neutron stars, which form from the core collapse of massive stars. But most neutron stars don't have magnetic fields this strong. Most have fields of only a trillion Gauss or so, still unimaginably powerful by terrestrial standards, but far weaker than magnetars. What makes certain neutron stars become magnetars? Recent research has suggested one possible answer, and it involves Wolf-Rayet stars. Remember HD 45166, the binary system we mentioned earlier? Observations have revealed that the Wolf-Rayet star in that system has an extraordinarily strong magnetic field for a massive star, about 43,000 Gauss. That's thousands of times stronger than the Sun's magnetic field, and it's strong enough that when the star eventually explodes and its core collapses to form a neutron star, the magnetic field will be conserved and amplified. When a stellar core collapses from something thousands of kilometers across to a neutron star just 20 kilometers in diameter, conservation of magnetic flux means the field strength increases by a factor of millions. A star with a 43,000 Gauss field collapsing to neutron star densities would produce a magnetar with a field strength in the hundreds of trillions of Gauss, exactly what we observe. This discovery has profound implications. It suggests that at least some magnetars come from massive stars that had strong magnetic fields to begin with. It provides a formation pathway that has been missing from our models, and it means that we can potentially identify future magnetars before they form by looking for massive, highly magnetized stars like the Wolf-Rayet component of HD 4166. But here's where it gets concerning from a planetary safety perspective. If Wolf-Rayet stars are progenitors of magnetars, and if Wolf-Rayet stars can produce gamma-ray bursts when they explode, then the formation of a magnetar might be associated with one of the most dangerous supernova types. The core collapse that creates the magnetar would also create the jets that produce the gamma-ray burst. And the magnetar itself, once formed, would be an ongoing source of powerful radiation outbursts for thousands or millions of years. Magnetars are relatively short-lived by cosmic standards. Their intense magnetic fields gradually decay over time scales of thousands to tens of thousands of years. As they age, the fields weaken, the radiation emissions decrease, and eventually, the magnetar becomes an ordinary neutron star or pulsar. But during their active phase, they're among the most energetic objects in the galaxy, regularly releasing bursts of energy that can be detected across the entire Milky Way. There's another class of magnetar-related phenomena worth mentioning: soft gamma repeaters. These are thought to be magnetars that undergo repeated, smaller starquakes, each one releasing a burst of soft gamma rays. Unlike the long-duration gamma ray bursts associated with supernovae, these bursts are brief, lasting only a fraction of a second, and they repeat irregularly over years or decades. But they're still dangerous if you're close enough. The 2004 burst from SGR 18620 temporarily interfered with satellites and spacecraft across the solar system. It saturated detectors on multiple observatories. It was the brightest event of its kind ever recorded, and it happened 50,000 light-years away. If a similar burst occurred from a magnetar only a few thousand light-years away, the effects would be proportionally more severe. At a few hundred light-years, it might pose a genuine threat to the biosphere. Fortunately, the nearest known magnetar to Earth, 1E 1048-5937, is about 9,000 light-years away, far enough to be safe from all but the most extreme outbursts. But magnetars are hard to detect. They're small, about the size of a city, and they only reveal themselves through their radiation emissions. There could be dormant or weak magnetars much closer that we simply haven't found yet. And there's this unsettling thought: every magnetar was once a massive star. Those stars formed somewhere, lived for a few million years, and then exploded. The magnetar that remains is the core, but the rest of the star's mass was ejected into space, forming an expanding nebula that eventually dissipates and becomes invisible. If you're looking at the sky and wondering where the dangers might be, you can't just look for bright, obvious stars. You have to consider that some of the most dangerous objects in the galaxy are invisible, dormant, waiting for the next starquake to announce their presence. Neutron star collisions and kilonovae. We've talked about individual stellar deaths, But what happens when two dead stars collide? Neutron stars sometimes form in binary pairs, two massive stars that lived and died together, each leaving behind a compact remnant. These pairs can survive for billions of years, orbiting each other, gradually spiraling closer as gravitational waves carry away their orbital energy. Eventually, the distance shrinks to zero. The two neutron stars, each about 10 to 20 kilometers across but containing 1 to 2 solar masses, collide at a significant fraction of the speed of light. The result is one of the most violent events in the universe, a neutron star merger. These collisions produce multiple phenomena, all of them dangerous in their own ways. First, there's the gravitational wave signal, ripples in space-time itself that propagate outward at light speed. These waves have been detected by observatories like LIGO and Virgo, confirming Einstein's century-old predictions about general relativity. The waves themselves aren't dangerous. They pass through matter essentially without effect. But they tell us that something catastrophic is happening. Then comes the electromagnetic emission. When two neutron stars merge, they release enormous amounts of energy across the spectrum. There's a bright flash of gamma rays, a short-duration gamma ray burst lasting only a few seconds. These bursts are similar to the long-duration bursts produced by collapsing massive stars, but they're formed by a different mechanism. The collision creates a rapidly spinning, highly magnetized object, possibly a more massive neutron star or a black hole, surrounded by an accretion disk of ultra-hot material. Jets of matter and radiation shoot out from the poles, and if one of those jets happens to be pointed at Earth, we see a gamma ray burst. Following the initial gamma ray flash comes the kilonova, a glowing cloud of radioactive material ejected during the collision. This material, rich in neutrons, undergoes rapid nuclear reactions, forming heavy elements like gold, platinum, and uranium. The radioactive decay of these freshly formed elements powers a visible light display that can last for days or weeks. Kilonovae are fainter than typical supernovae, but still bright enough to be seen across billions of light years. The danger from neutron star mergers is twofold. First, there's the immediate threat of the gamma ray burst, which, like those from collapsing stars, can be dangerous across thousands of light years if pointed our way. Second, there's the long-term increase in cosmic ray flux from the expanding debris, which can persist for thousands of years and contribute to elevated radiation levels in nearby star systems. But there's good news, relatively speaking. Neutron star mergers are rare. Current estimates suggest they occur in the Milky Way only about once every 10,000 years, making them 100 times less frequent than supernovae. And because neutron stars are small and faint, the mergers typically happen in regions where we're not looking, discovered only when their gamma ray bursts or gravitational wave signals announce their presence. Still, the statistical odds suggest that over the past few billion years, Earth has probably been within the danger zone of at least one nearby neutron star merger. The evidence, if any remains, would be subtle: a spike in radioactive isotope deposition, a temporary disturbance in the fossil record, possible climate effects from altered atmospheric chemistry. Teasing out these signals from the noise of geological processes is extremely difficult. One fascinating aspect of neutron-star mergers is their role in creating the heavy elements we find on Earth. All the gold in your jewelry, all the platinum in catalytic converters, the uranium in nuclear reactors. Much of it came from neutron-star collisions. These rare, violent events are cosmic forges, synthesizing elements that cannot be created in any other way. The gold in a wedding ring represents atoms that were once inside neutron stars, compressed to nuclear densities, hurled into space at relativistic speeds during a collision, scattered through interstellar gas clouds, incorporated into a new stellar system, and eventually finding their way to Earth. It's a beautiful story of cosmic recycling, but it comes with a price. The same processes that give us gold also produce deadly radiation. The jets from neutron star mergers can sterilize regions of space. Planetary systems caught in the path of a nearby merger would be scoured of life, their atmospheres blasted away, their surfaces irradiated. And here's an uncomfortable truth. We can't predict neutron star mergers. We can't see neutron star binaries until they do something to announce their presence, and by then it's far too late. Most neutron stars don't emit much radiation. They're invisible to our telescopes unless they're pulsars, beaming radio waves in our direction as they rotate, or unless they're accreting material from a companion star. Binary neutron star systems can lurk undetected in the galactic darkness, spiraling closer and closer, until the moment of collision releases enough energy to briefly outshine the entire galaxy. Somewhere in the Milky Way, right now, there are neutron star binaries that will merge within the next million years. Some of them might be only a few thousand light-years away. We don't know where they are. We don't know when they'll merge, and we won't know they're a threat until the gravitational waves and gamma rays are already on their way. The Ordovician extinction, a gamma-ray murder mystery. Now, let's travel back in time, not to a distant star, but to Earth itself, 440 million years ago. The planet looked very different then. Life was almost entirely oceanic. The land was barren, inhabited only by primitive plants and arthropods. But the seas teemed with diversity. Trilobites, brachiopods, graptolites, and early fish. This was the late Ordovician period, a time when marine life was flourishing, experimenting with new forms, filling ecological niches that had never before been occupied. And then, suddenly, it ended. Within a span of perhaps a few 100,000 years, geologically instantaneous, roughly 60% of all marine species went extinct. Entire families of organisms vanished from the fossil record. Reef ecosystems collapsed. The diversity that had taken millions of years to build was decimated. This was the first of the Big Five mass extinctions in Earth's history, and for decades, scientists have puzzled over what caused it. There's evidence for climate change during this period. The Earth underwent a significant cooling, with ice sheets expanding from the poles. Sea levels dropped, exposing continental shelves and fragmenting marine habitats. But what triggered the cooling? Why did it happen so rapidly? And why did it affect marine life so disproportionately compared to the sparse terrestrial life of the time? One hypothesis: proposed by several researchers over the past 2 decades, is that a gamma-ray burst struck Earth during the late Ordovician. The evidence is circumstantial but intriguing. A gamma-ray burst would explain the rapid onset of the extinction. Unlike gradual climate change or asteroid impacts, which leave clear geological signatures, a gamma-ray burst would arrive with no warning and leave almost no physical trace beyond its biological effects. Here's how it might have worked. A massive star or a neutron star binary, somewhere within a few thousand light-years of Earth, exploded or merged. The gamma-ray jet from the event was pointed toward the solar system. When the radiation arrived, traveling at light speed, it slammed into Earth's upper atmosphere, initiating a cascade of chemical reactions. Nitrogen and oxygen molecules were split apart by the high-energy photons. Nitrogen oxides formed in abundance. And the ozone layer, Earth's shield against ultraviolet radiation, was depleted. With the ozone layer compromised, ultraviolet radiation from the sun poured through to the surface. In the oceans, this would have been devastating. Phytoplankton, the foundation of the marine food web, are extraordinarily sensitive to UV radiation. They live in the upper layers of the ocean where light can penetrate, and they have no way to hide from increased UV. A gamma-ray burst would have caused a mass die-off of phytoplankton across the globe. The effects would cascade up the food chain. Zooplankton that feed on phytoplankton would starve. Small fish and filter feeders that depend on zooplankton would follow. The entire marine ecosystem, from the base to the apex predators, would collapse. Reef-building organisms, already stressed by changing ocean chemistry and temperatures, would die off. The fossil record would show a sudden drop in diversity, exactly what we observe at the end of the Ordovician. On land, the effects would be less severe. Terrestrial life in the Ordovician was sparse and largely confined to moist environments where UV radiation could be partially blocked by water or primitive vegetation. Many terrestrial organisms had natural UV protection that marine life lacked. This would explain why the extinction hit marine ecosystems so much harder than terrestrial ones. There's another piece of evidence: nitrogen isotopes in ancient rocks. The chemical reactions initiated by gamma rays would preferentially affect certain nitrogen isotopes, leaving a signature that could, in theory, be detected in geological samples. Some studies have reported anomalies in nitrogen isotope ratios from rocks deposited during the late Ordovician, though the interpretation of these data remains controversial. But here's the challenge. Proving that a gamma-ray burst caused the Ordovician extinction is nearly impossible with certainty. The event happened so long ago that most direct evidence has been erased by geological processes. We can look for consistent signatures, we can build models, we can compare the expected effects of a gamma-ray burst with what we see in the fossil record. But without a time machine, we can never be absolutely sure. What we can say is that the probability calculations support the hypothesis. Over the past 500 million years, covering the period since complex life became abundant on Earth, the statistical likelihood of a nearby gamma-ray burst is roughly 50%. Go back further to the 4 billion years since life first appeared, and that probability rises to 90%. It's more likely than not that Earth has been struck by biologically significant gamma-ray bursts multiple times in its history. The Ordovician extinction might have been one such event, or it might have been caused by something else. Volcanic eruptions, asteroid impacts, changes in ocean circulation. We may never know for certain, but the possibility that it was caused by a dying star thousands of light years away, an event that had nothing to do with conditions on Earth yet reached across the galaxy to touch our world, is both humbling and terrifying. It reminds us that Earth is not isolated. We live in a galaxy full of violence, full of energetic events that can reach across vast distances. Our planet's history has been shaped not just by local processes, by evolution and geology and climate, but by cosmic accidents, by the bad luck of being in the wrong place when a distant star exploded. And it could happen again. The next gamma ray burst in our galactic neighborhood might arrive tomorrow or a million years from now. We wouldn't see it coming. We couldn't stop it. The first sign would be the burst itself, a flash of gamma rays that would peak and fade in seconds, followed by the slow unraveling of the ecosystem as ultraviolet radiation took its toll. Our galactic safe zone. Given all these dangers, stellar explosions and gamma-ray bursts, and neutron star collisions, you might wonder how life on Earth has survived at all. The answer lies partly in luck and partly in location. As we mentioned earlier, Earth orbits in what seems to be a relatively safe region of the galaxy, and understanding why this matters can give us perspective on both the dangers we face and the stability we enjoy. The galaxy is not uniform. Star formation happens primarily in the spiral arms, where giant molecular clouds provide the raw material for new stars. These regions are dense with young, massive stars, the very stars that will explode as supernovae or produce gamma-ray bursts within just a few million years. If Earth were located in one of the spiral arms, we would be exposed to these dangers much more frequently. Estimates suggest that star systems in the arms experience supernova rates 10 to 100 times higher than systems in the spaces between the arms. But we're not in a spiral arm. We're in the Orion Spur, a minor structure between the Sagittarius and Perseus arms. This spur contains fewer massive stars and has a lower rate of star formation. It's quieter, more stable, less prone to the violent events that plague the denser regions of the galaxy. This alone has probably contributed to Earth's long-term habitability. There's another factor, our orbital radius. At about 26,000 light-years from the galactic center, we're far enough from the core to avoid the intense radiation environment there, but not so far that we're in the metal-poor outer halo, where rocky planets might have trouble forming. And we orbit close to what's called the corrotation radius, where our speed around the galaxy matches the rotational speed of the spiral density waves. This means we tend to stay between spiral arms rather than passing through them frequently. The Sun's orbit isn't circular. It oscillates above and below the galactic plane and moves slightly inward and outward over time. But, on average, we spend more time in the relatively safe inter-arm regions. This reduces our exposure to supernovae and other stellar hazards. The Sun also bobs up and down through the galactic plane with a period of about 60 million years. Some, Researchers have suggested this vertical oscillation might correlate with mass extinction events on Earth. The idea is that when the Sun passes through the denser parts of the galactic disk, we encounter more dust, more molecular clouds, and possibly more comets from the Oort cloud being disturbed by nearby stars. These encounters could trigger comet showers, leading to increased impact rates on Earth. The evidence for this correlation is debated. Some studies find a weak signal connecting disk crossings to extinctions. Others find no correlation at all. But it's an intriguing possibility that our galactic environment, not just conditions on Earth, influences the long-term history of life. Right now, looking at the current census of nearby stars, we can identify the potential threats. We've mentioned Betelgeuse, IK Pegasi, and a few others. None of them are in position to harm us if they explode in the near future. The nearest Wolf-Rayet stars are hundreds of light-years away. The nearest known magnetars are thousands of light-years distant. The massive stars in the Scorpio-Centaurus Association, one of the nearest regions of recent star formation, are mostly more than 400 light-years away. In other words, for the next few thousand years at least, we're probably safe from immediate stellar threats. There are no ticking time bombs in our immediate cosmic neighborhood, no massive stars poised to explode and pointed our way, no neutron star binaries about to merge. But that's probably. There's always uncertainty. New discoveries happen regularly. In 2023, astronomers identified HD 45166's strong magnetic field, revealing it as a future magnetar. Who's to say there aren't other hidden threats we haven't yet discovered? White dwarfs in binary systems that we've overlooked. Distant Wolf-Rayet stars whose jets are aligned with Earth. Neutron star binaries too faint to detect until they merge. The galaxy is vast, and our surveys, while impressive, are far from complete. We know the locations and properties of millions of stars, but the Milky Way contains hundreds of billions. Most are too faint, too distant, or too obscured by dust for us to study in detail. The census of stellar hazards is ongoing, and every year brings new discoveries, new candidates, new objects to monitor. And even if we knew every threat in the galaxy right now, stellar motions mean the situation will change. In 1,000,000 years, some currently distant stars will have moved closer. New massive stars will have formed in nearby molecular clouds. Old threats will have exploded or moved away. The cosmic neighborhood is dynamic, constantly reshaping itself. This is the nature of living in a galaxy. Safety is contingent, temporary, statistical. We can estimate the odds. We can identify the nearest dangers, but we can't eliminate the risk entirely. The universe, for all its beauty, remains a dangerous place, and Earth's long-term survival depends on a combination of continued good fortune and, eventually, our ability to spread beyond this single fragile world. Closing, living under cosmic threat. And so we've journeyed together through the complete catalog of stellar dangers, from the focused beams of gamma-ray bursts that can cross thousands of light-years without losing their lethal potency, to the spectacular deaths of massive stars in supernova explosions that briefly outshine entire galaxies, from Wolf-Rayet stars spinning toward their explosive ends to magnetars with their reality-warping magnetic fields, and neutron star collisions that forge precious metals in the crucible of their destruction. We've seen, in detail that might seem almost overwhelming, how these cosmic catastrophes could, under precisely the wrong circumstances, threaten or even completely end life on Earth. We've explored the mechanisms, understood the physics, calculated the probabilities, and examined the evidence that such events may have affected our planet multiple times in the deep past, leaving subtle traces in rocks and fossils, perhaps even triggering some of the mass extinctions that punctuate the history of life on our world. It's a sobering picture, undeniably. The universe is vast and beautiful, but it's also violent and dangerous on scales that make terrestrial disasters seem trivial by comparison. And yet, here's something remarkable to consider as you feel your consciousness beginning to drift toward sleep. Despite all these dangers, despite gamma-ray bursts and supernovae and magnetar outbursts, despite every cosmic threat we've discussed tonight, life on Earth has not just survived but thrived for nearly 4 billion years. That's not an exaggeration for effect. 4 billion years. That's 4,000 million years, 40,000 centuries, millions of generations of living things reproducing, evolving, adapting, competing, cooperating, building ecosystems of stunning complexity. Through multiple mass extinctions, some triggered by asteroid impacts, some by volcanic eruptions, possibly some by cosmic events we've discussed tonight, through countless nearby supernovae whose radiation washed over our world, depositing their radioactive signatures in ancient sediments, through whatever cosmic hazards the galaxy has thrown at us over the eons, life has adapted, recovered, and continued. The biosphere has proven itself remarkably resilient, almost stubbornly persistent in its determination to exist. Evolution, that patient, relentless force, is creative beyond imagination, constantly generating new forms, new strategies, new ways of surviving. And while individual species come and go, while entire families and orders of organisms have been wiped out by catastrophes both terrestrial and cosmic, the thread of life itself has proven remarkably, almost miraculously, difficult to break completely. Even the worst extinction events, the ones that eliminated 90% or more of all species on Earth, left survivors. And those survivors, given time measured in millions of years, but time nonetheless, eventually rebuilt biodiversity, filling empty niches, radiating into new forms, sometimes creating ecosystems more complex and diverse than what existed before the catastrophe. Tonight, as you rest, as your muscles relax and your breathing slows, and your thoughts become less linear, less demanding, consider this comforting fact. The statistical odds of a truly catastrophic stellar event affecting Earth in any given year, or even in any given century or millennium, are vanishingly, astronomically small. You personally are more likely to win multiple lotteries, to be struck by lightning multiple times, or to experience any number of other extremely low probability events than you are to witness a nearby gamma-ray burst or supernova that threatens life on our planet. The galaxy is enormous, containing perhaps 400 billion stars spread across a disk 100,000 light-years wide. The vast majority of those stars are too small to ever explode as supernovae. And even among the massive stars that will explode, the vast majority are far enough away that their explosions pose no threat whatsoever to us. But here's the other side of that statistical coin, the part that adds a certain poignancy to our existence. Over millions of years, over tens of millions of years, over hundreds of millions of years, those tiny probabilities accumulate. They add up. Low probability events, given enough time, become not just possible but likely, then inevitable. It's not really a question of whether Earth will face another stellar threat of the magnitude we've discussed tonight. It's a question of when. Will it be 1,000,000 years from now? 10 million? 100 million? We don't know, can't know. The universe doesn't give us advance warning for these things. The only way we'd know a gamma-ray burst was coming would be when it arrived, traveling at light speed, impossible to detect before it was upon us. And when that day comes, whenever it is, whether it's in the relatively near future or the incomprehensibly distant future, life on Earth will face it the same way life has always faced catastrophe throughout the 4 billion-year history of our planet. By adapting, if possible, or perishing if adaptation proves impossible, and leaving behind whatever survivors are hardy enough, lucky enough, or flexible enough to make it through to the other side. If we're fortunate, if we as a species show the wisdom and foresight that our intelligence supposedly enables, we'll have expanded beyond Earth by then. We'll have established self-sufficient populations on other worlds, in space habitats, perhaps even around other stars. In that case, even if Earth itself were sterilized by a cosmic catastrophe, humanity and whatever other terrestrial life we bring with us would survive. Our story would continue, written in the skies of other worlds, ensuring that at least one line of Earth's evolutionary heritage persists into the far future. If we're still confined to this single planet when the next major cosmic threat arrives, then our fate will be inextricably tied to Earth's fate. We'll have to hope, as life has hoped before, that whatever event occurs happens far enough away, is weak enough in its effects, or misaligned enough in its aim to leave us intact. Damaged, perhaps, but not destroyed. Challenged, but not eliminated. And given life's track record, given its remarkable resilience over billions of years, there's reason for cautious optimism even in the face of cosmic dangers we cannot control or prevent. But here's something to hold on to as you drift deeper toward sleep. As consciousness becomes less focused and more dreamlike, as the boundaries between waking and sleeping blur, right now, at this precise moment in cosmic history, we're safe. Genuinely, verifiably safe. The stars that could harm us if they exploded tomorrow are distant, separated from us by hundreds or thousands of light years of empty space. The massive stars in our immediate galactic neighborhood, the ones close enough that we can study them in detail with our telescopes, are well behaved, stable, showing no signs of imminent catastrophic collapse. No gamma-ray bursts are currently speeding toward us through the darkness, their deadly radiation approaching at light speed. No magnetars within threatening distance are erupting with lethal bursts of X-rays and gamma rays. No nearby neutron star binaries are spiraling toward merger. For this moment, for this night, for this year and decade, and likely for many centuries or even millennia to come. Earth floats peacefully through space, a beautiful blue and green gem wrapped in swirling white clouds, orbiting a remarkably stable, remarkably well-behaved, middle-aged yellow star, protected by a thin but effective blanket of atmosphere that shields us from almost everything the universe can throw at us. The cosmos is vast, old, almost beyond human comprehension, and undeniably full of violence on scales that dwarf anything we experience on Earth. Stars live and die in explosions that release more energy in seconds than our sun will produce over its entire multi-billion-year lifetime. Galaxies collide in slow-motion cataclysms that take millions of years to unfold, scattering stars like sparks from a cosmic forge. Black holes merge, releasing gravitational waves that ripple through the very fabric of space-time itself. Neutron stars spin hundreds of times per second, their surfaces crawling with magnetic fields strong enough to tear apart matter at the atomic level. The universe is a place of extremes, of physics pushed to its absolute limits, of energies and densities and temperatures that make terrestrial phenomena seem gentle by comparison. And yet, here we are. Improbable aggregations of carbon and nitrogen and oxygen and trace elements, arranged in patterns complex enough to be self-aware, conscious enough to look up at the night sky and wonder about our place in it all. We're made of stardust, quite literally, our bodies built entirely from elements forged in stellar cores billions of years ago and scattered by supernova explosions that happened long before our sun even existed, long before the solar system condensed from its primordial cloud of gas and dust. We are survivors of cosmic catastrophes we don't even remember, descendants of organisms that weathered asteroid impacts and massive volcanic eruptions and ice ages, and whatever stellar threats happened to come Earth's way over the past 4 billion years. Our lineage, stretching back through mammals and reptiles and fish and invertebrates and single-celled organisms all the way to the very first self-replicating molecules that appeared in Earth's ancient oceans, has survived everything the universe has thrown at it so far. And tomorrow night, or 1,000 years from now, or 1,000,000 years from now, when another massive star somewhere in the Milky Way reaches the end of its life and explodes, sending jets of gamma radiation screaming through space at light speed. Or when a magnetar undergoes a massive starquake and releases more energy in a fraction of a second than the sun produces in a year. Or when 2 neutron stars finally spiral together and collide in a blinding flash of gravitational waves and gamma rays. Perhaps that beam will miss us, passing harmlessly by, just another cosmic event in a galaxy full of them, invisible except to our telescopes and detectors. Perhaps it will be too far away to pose any threat, its energy diluted by distance, until it arrives at Earth as nothing more than an interesting astronomical phenomenon for scientists to study. Perhaps we'll be lucky once again, as we've been lucky so many times before throughout the history of life on our world. Or perhaps not. Perhaps someday, on a timescale we can't predict with any certainty, the cosmic lottery will turn against us. Perhaps a gamma ray burst will find Earth precisely in its crosshairs, pointed at us by sheer random chance. Perhaps the ozone layer will fail under the onslaught of high-energy radiation, and life will face another existential test, another filter through which only the most adaptable and fortunate will pass. And if that happens, if and when that happens, we'll discover, as life has discovered before during every mass extinction and catastrophe that has punctuated Earth's history, whether we have what it takes to endure, to adapt, to survive. We'll learn whether our intelligence, our technology, our ability to understand and predict and prepare gives us any advantage over the blind forces of cosmic destruction, or whether we're just as vulnerable as any other form of life when faced with energies on scales that make human concerns irrelevant. But tonight, under these stars, in this moment, we're here, alive, conscious, aware of both the beauty and the danger. And that awareness, that ability to look up at the night sky and understand what we're seeing, to recognize both the majesty and the threat, that's what makes us human. We're the universe looking at itself, wondering about its own nature, calculating the odds of its own survival. Sleep well. Dream of stars, if you like. Dream of distant supernovae blooming in the dark, of neutron stars colliding in fountains of gold, of magnetars singing their electromagnetic songs across the galaxy. These events are real. They're happening out there right now, at this very moment, too far away for us to see, too distant to threaten us. But they're part of the same universe we inhabit, governed by the same laws of physics, made of the same fundamental particles. And in understanding these cosmic dangers, in learning how stars die and how their deaths can reach across incomprehensible distances of space to touch other worlds light years away, we're doing something genuinely remarkable, something that speaks to the highest aspirations of human consciousness. We're preparing, not necessarily in any immediate practical sense, because we can't shield Earth from a gamma-ray burst or deflect the radiation from a nearby supernova. But we can understand the risks with mathematical precision. We can calculate probabilities and estimate timescales. We can truly appreciate, how fortunate we've been to exist during this particular quiet interval in cosmic history. This brief window between stellar catastrophes when our corner of the galaxy happens to be relatively safe. And perhaps most importantly, we can recognize that our long-term survival as a species, our ability to persist not just for centuries but for millions of years into the future, may ultimately require us to become something more than mere inhabitants of a single fragile world. It may require us to spread outward, to establish populations on multiple worlds, in space habitats, perhaps eventually around other stars entirely, ensuring that no single cosmic event, no matter how energetic or catastrophic, can extinguish the light of consciousness entirely, can erase the universe's ability to know itself through us. For now, though, in this moment, rest. Let the weight of these thoughts, heavy as they might seem, carry you gently toward sleep like a river carrying a leaf toward the sea. You're safe here, tonight, on this ancient world that has survived 4 billion years of cosmic bombardment and catastrophes we can barely imagine, that has weathered asteroid impacts and volcanic eruptions and ice ages and supernovae and probably gamma-ray bursts and every other hazard the universe could devise, and yet continues to orbit peacefully around its stable yellow star. The stars will still be there tomorrow morning when you wake, beautiful and dangerous in equal measure, distant and seemingly eternal, despite the fact that they're all dying on various timescales, watching over us in their indifferent way as we make our uncertain way through the cosmic dark, trying to understand our place in this vast and dangerous and utterly beautiful universe. If tonight's journey through the dangerous stars has sparked your curiosity or helped you unwind and drift toward peaceful sleep, I sincerely hope you'll consider liking and subscribing to the Sleepy Science Society. These quiet explorations of the universe, these gentle investigations into cosmic mysteries, both beautiful and terrifying, help more people find their way here. One restful mind at a time, one curious soul at a time. Sweet dreams, and may the stars be kind.